So let's start. We solve this paper here. Okay, so the first exercise says that you have the power series given by, so the sum, let me take the blue one. So we have sum n going from 2 to infinity of 1 over n log n multiplied by x plus 1 to the power n, right? Then converges for every x in interval from -2 to 0, converges for every x in interval for every x belonging to R, is absolutely convergent for every x in interval -2 to 0, is convergent but not absolutely convergent. Okay, remind that when you are given a power series, the power series in general, it's sum n starting from sum n0 to infinity of you have sum an multiplied by x minus x0 to power n. This is the form of a power series, right? This x0 here is the center. Okay, then they told you in theory that a power series converges or converges absolutely in the following interval: x0 minus r and x0 plus r. Then this may be included or excluded, or like this may be also included or excluded, right? This is, but what is r? R is actually 1 over the limit as n tends to infinity of an plus 1 over an in absolute value, right? This is exactly how you got the interval of convergence of a power series. In our case, an is 1 over n log n. And thus an plus 1 is 1 over n plus 1 log of n plus 1. So let's find r. If we get r is excuse me, here I made a mistake. So the logarithm here is in the, so basically we have n plus 1 multiplied by the logarithm of n plus 1, right? So if one do an plus 1 over an, what comes out? It comes out that it will have an plus 1, which is 1 over n plus 1 multiplied by the logarithm of n plus 1, divided by an means multiply by n log n over 1. So at the end, an plus 1 over an gave us just let me write n over n plus 1 multiplied by the logarithm of n over the logarithm of n plus 1. Okay, now if I do the limit when n tends to infinity of this will lead to n over n, because I take the most important, multiply by the log of n over the log of n, because also here n is 1 is negligible. So we reach that this limit is 1, right? Then it means that the radius of the power series will be 1 over 1 equal to 1. So we know now that the center, I remind that the center of this power series was -1. Okay, the center of this power series, so we have x minus x0. So for this power series, the center is x0 equal to -1. Is that clear? So going back, we are sure that this power series converges absolutely in the interval. It was the center minus the radius, so it's the center, so -1 minus 1 comma minus 1 plus. So it converges absolutely in the interval minus 2 to 0, right? Now we need to check it when x equal to 2 and x equal to 0. Okay, so first let's go in the answer and see if is there any answer saying that the series converges here. So converges for every x in the interval. No. So here they didn't take minus 2 and they take 0. Yes or not? So we need to check. Let's start, as we can say, let's take for example, let's start from 0. So if I put x equal to 0, so if x is equal to 0, the series I get becomes sum of 1 over n log n, right, multiply by 1 to power n, and thus I get the series sum n going from 2 to infinity of this is 1 over n times the logarithm of n. Is that clear? Now this series here is what I want to know. Is it convergent? Is it divergent or not? So there is a criteria that tell us about the convergence of the series of the type. So I know that you saw in class that if you are sum of n to power alpha, if alpha is bigger than 1, then converges, right? If alpha is less or equal than 1, the series diverges. It's like the improper integrals. Then, but in more general, there is a more general criteria about 1 over n to power alpha multiplied by the logarithm to power beta of n. You saw it in class, yes or not? Okay. To make sure that it is clear, because it has been a long time I haven't used it, so let's go and discover it together. But you should make, so it is called harmonic, generalized harmonic. So generalized harmonic, it should be, I think, like this, harmonic series. Okay, the generalized harmonic series, we should see it somewhere. Okay, and we shall see it somewhere. Because here there is only the harmonic series. Okay, just for the moment, harmonic series. Here I took harmonic numbers. History, divergence. Okay. It should be somewhere. Okay, but I need the general theorems, not just the specific case. By the way, I think I remember the theorem. Never mind. So I wanted to let you see it by yourself, but the theorem is like this. So in the most general case in which you have, so if you have this case, you already know how to deal with it, okay? But in the most general case, in which not only you have 1 over n to power alpha, so look, if alpha, okay, is bigger than 1, or alpha equal 1 and beta is bigger than 1, the series converges. So it is, or this condition, so if this condition hold independently on beta, the series will converge. Otherwise, if alpha is 1 and beta is greater than 1, the series converges. Is that clear? Either this or this. Is that clear? If alpha is smaller than 1, or alpha equal 1 and beta is smaller than 1, here, or this, the series diverges. Okay, in our case we have sum 1 over, okay, this is even smaller or equal, I think. Okay, this is also here alpha smaller or equal. So we have n multiplied by log of n, right? And so alpha is 1 and beta is 1, so diverges. Okay, so we have that 0 should, so now we are sure that our set is 0 excluded. No, I mean it's from -2 to 0. 0 is excluded, but -2 can still be include, right? We go now and study when x equals to -2. If we put x to be -2, the series will be sum of 1 over n log n, right, multiplied by -2 plus 1, which is -1 to power n. Now actually n going from 2 to infinity. This is what we call the so-called alternating term series. The alternating term series, that is make like sum of sum an multiplied by -1 to power n, with the condition that an is greater than 0. These are called alternating term series. And what can we use to prove the convergence of an alternating term series is the Leibniz criteria. The Leibniz criteria says that if an tends to 0 and an is decreasing, then this series converges. Is that clear? In our case, an is 1 over n log n. That clearly tends to 0 as n tends to infinity. Furthermore, it's clear that an is decreasing. Why is it decreasing? I mean, what is to make sure that a sequence is decreasing if an plus 1 is smaller than a? Yes or not? If you do an plus 1 here, it will be 1 over n plus 1 multiplied by the logarithm of n plus 1. You are comparing it to 1 over n log n. Pay attention that n plus 1 is bigger than n. Log of n plus 1 is bigger than log of n. So at the end, you are doing 1 divided by something higher than what you are dividing than the stuff. So the denominator here is bigger than the denominator here, and hence this stuff is smaller than this. So an plus 1 is smaller than an, so it is decreased. The sequence is decreased. So by Leibniz, the following series converges. Is that clear? So our set of convergence is -2 included until 0x excluded, right? Turning back to the possibility, it says that the series is absolutely convergent for every x in this interval. So the answer is C, right? Oh. Any question? Or keep in mind that when in the interval x minus x, when the when the power series converge, when the power series, excuse me, I made no, pay attention. It's convergent because look, we made a small mistake here. The power series converges absolutely in the interval x0 minus r to x0 plus. Okay, it's clear or it's not clear? So we know that the power series will converge absolutely in the interval from -2 to 0. Now when you check at 2, we saw that it converged at -2, but we didn't check if it converges absolutely at -2. In this here, it converged absolutely. It's the theorem. But when we check at 2, we just saw that it converges. Because if you try to check the absolute convergence at -2, it will give you the series absolute value of 1 over n log n times -1 to power n, yes or not? But this absolute, it will be 1 over n log n multiplied by 1 -1 power n. N is 1, but we know that it is divergent. We saw it before, right? So the series converges in this interval, but not absolutely, because of at the point -2. So going back, so it's convergent but not absolutely convergent for every x in this interval. Do you have any question? Yes, absolutely. We saw that it converges absolutely in the interval from -2 to 0. Then we check the convergence at -2, right? And see that it converges also at -2 to 0. But when we check the absolute convergence at -2, we see that the absolute convergence doesn't hold at -2. That's why we say that it converges in this interval, but as the absolute convergence do not hold at -2, we will say it converges in this interval but not absolutely convergent at each point in this interval. So the answer is 1D. Okay, so pay attention to the traps. Okay, now you are given the function f of x equal to f of xy equal to, so let me close this. You have the function f of xy equal to, it is x over 1 plus x squared plus y squared. Nice. So has a unique stationary point, which is a saddle point, has a unique stationary point, which is a local minimum point, has 2 stationary points, and has no stationary points. So let's find what are the. So when I have a function, what is the stationary point? What is a stationary point? A stationary, when I have my function, first I compute the gradient of f. That will be the derivative of f with respect to x and the derivative of f with respect to a point. Then the point with component x0 and y0 is a stationary point, yes or not? If the gradient at that point give the null vector, It's like when the derivative give in the a point x0 y0 is a stationary point if the gradient computed at that point give the null vector. So let's go and find the gradient of this function. To find the gradient of this function, I need to do the derivative of f with respect to x. The derivative of x with respect to x will be 1 plus x squared plus y squared all square, right? And then this will be 1 multiplied by 1 plus x squared plus y squared minus the derivative of the numerator of the denominator with respect to x is just 2x, right? Multiply by x. So the derivative of this function with respect to x is 1 plus x squared plus y squared minus 2x squared divided by 1 plus x squared plus y squared, right? Equal to 1 plus y squared minus x squared, 1 plus y squared minus x squared divided by 1 plus x squared plus y squared. Then the derivative of f with respect to y, mind that what f is this function. The derivative of f with respect to y will still be 1 plus x squared plus y all square. No, here this is all square. This is all square and this is all square. The derivative with respect to y will still be 1 plus x squared plus y squared all square. Then it will be 0 multiplied by 1 plus x squared plus y squared minus the derivative of this with respect to y is 2y multiplied by 2y multiplied by x. So it's going to be minus 2xy over 1 plus x squared plus y squared all square. So our gradient, the gradient of the function f is 1 plus y squared minus, so 1 plus y squared minus x squared. Let me just say over the denominator because by the way we know it, comma minus 2xy over 1 over the denominator. Okay, so let me, now that we have the gradient, let's go back on the questions. The question says that has a unique stationary point, has a unique stationary point, that is has two stationary points, has no stationary points. Let's go and see the number of stationary points. I say that the stationary point are the point that make the gradient equal to 0. So to solve for the stationary, we have to say 1 plus y squared minus x squared over d equal to 0, and 1 and then minus 2xy over d equal to 0, right? But the denominator can be equal to 0, so we have 1 plus y squared minus x squared equal to 0, and let's say minus 2xy equal to 0. That means 2xy equal to 0. This equation here leads to x equal to 0 or y equal to but these are two cases, yes or not? This equal to 0 or now we solve. If x is 0, what will be? Okay, so if x is 0, the first equation will become 1 plus y squared equal to 0. That's no solution, yes or not? But if y is 0, we have 1 minus x squared equal to 0. Thus x is plus or minus 1. So there is the point A which has component 1, 0, and the point B having component minus 1, 0. That are my two stationary points. Is that clear? So going back here, we have that in fact the function has two stationary points, and thus the answer is 2C. Okay, Nice, we stop here for this video and then we continue in the next section.